and welcome to another lecture of thermodynamics for energy and mineral engineering. Today I am going to remind you of the supplemental reading that you have assigned to you inside of your Canvas content management system. I've got a link to Professor Emeritus Frank Lambert's work on redefining entropy in terms of the basic idea that entropy is not disorder. It's all about the dispersal of energy. And you've got a modern thermodynamics reading from Entropy that is chapter 3, pages 89 to 104, really supplementing ideas about thermodynamics and dealing with what we are covering today, which is the Prigogine formalism of the instantaneous change of entropy, ds. You're going to find that Entropy reading in your Library Resources tab in Canvas within the e-reserves. So, let's get going. Basically, if you're reading inside of Koretsky, you're seeing that the ideas of thermodynamics are presented, they don't seem to be as exciting necessarily as what I'm suggesting inside of your lecture notes. And part of that is that there's a major change that's happened inside of thermodynamics in the last 30, 40 years that is dealing with the ideas of, largely founded by Dr. Ilya Prigogine, who won the 1977 Nobel Prize in Chemistry, former professor at UT Austin, and whom passed away in about 2003. In 2003, yes. So he has the Prigogine convention for the instantaneous change of entropy, ds, that we're looking at today. So how does that work? Well, if I were to look at entropy change, and in this case you're going to notice that I've got entropy change as ds, that is a capital letter S, and that capital letter S is really best signified in my notes as having a little dash up at the top of the S, just to distinguish that we're talking about an extensive form of entropy change. So we know that when we have an extensive state variable or state, we can add the parts together. So I've got an extensive state that I'm adding together, and I'm going to add together the parts of the incremental change of entropy that are going to be associated with two things. This is very different than Koretsky, so bear this in mind. You see I've got DES and I've got plus DIS. DES is the external exchange of entropy. That's entropy exchange across the boundary. Just like we would have thought of energy exchange across the boundary, this is entropy exchange across the boundary, plus any entropy changes internal to the system, DIS. So E for exchange, I for internal. So again, that is E for exchange, I for internal. All right. Now, if I look at that and I write out the Clausius version of the first law of thermodynamics, you're going to see that the first law of thermodynamics, no matter what, would be ds is equal to, for a known path, would be dq relative to the temperature of the surroundings. And by known path, I mean, like, you see that q is a path-dependent function. The Prigogine adds this functionality to the description to say, okay, if we knew the path of q, we would give it an exact differential for that specific case. So that's why you're seeing a unique version of the instantaneous change of q in this particular equation. But dq can be rewritten. So the instantaneous change of heat, exchange of heat, can be rewritten as du plus pdv. Okay, that's du plus pdv divided by the temperature of the surroundings. If I were to diagram a system, okay, if I were to diagram a system of system and surroundings, I'm going to diagram it as a circle in this case. So when I'm doing diagramming of energy exchange for a system, you've seen this standard box, right? But now I'm going to diagram a system and only follow the entropy changes, in which case I'm using a circle. This is just my convention in the class. So if it's still a simple system and surroundings and a boundary, and system is on the inside, surroundings are on the outside, the circle is the boundary. But it allows me to show that the DES, that external exchange, or the exchange of entropy across the boundary, is right there diagrammed with the squiggly arrows back and forth, could go either direction, and DIS is contained within the system, right? So if DES, as you will see in your supplemental reading, can be defined as the du plus PDV divided by T, then we need a way to format the internal entropy changes to the system. And those internal entropy changes to the system, that DIS, is going to be formed in a very fundamental way as force times displacement. So generally some force, some driving, motivating force times instantaneous displacement. That's DIS. And those values of DIS, those values will always add together to be greater than or equal to 0. What we're going to do is we're going to be repeating this in the future lectures. So just take a look at this. This breakup of the Clausius relationship has been now broken up into exchange of entropy across the boundaries, DES, and internal entropy change inside the system. Okay. So when we started, when we finished last lecture, we were talking about adiabatic processes. We were talking about processes that are reversible and irreversible, and how do we address analysis between irreversible and reversible systems. Well, we know that an adiabatic system is defined, let's say this again. An adiabatic process is defined as Q equal to 0. It's not an isothermal process. In fact, because it is adiabatic process, temperature can and pretty much must change, because we have to get the energy for the internal energy change somewhere, and you can't get it from the boundary, so you're going to get it from temperature change in the gas itself. You're going to suck the energy out of the gas or dump the energy back into the gas. If I look at this back at Koretsky, I'm going to have now intensive entropy change, 3.3 on page 134. And that's going to be represented as the delta S of the universe is going to be equal to all the entropy change in the system plus all the entropy change in the surroundings. Now, of course, one would argue that potentially we would just write this as an extensive form, but we'll roll with it from here. Inside of Kondapudi, there's a very similar relationship of ds equal to the entropy change inside of the system plus not the instantaneous change of entropy in the surroundings, but the instantaneous entropy exchange across the boundary is what we are going to be talking about, which is really just another way of keeping your eye on the ball. The ball is the system, and so we follow the energy exchanging across the boundary in the Kondapudi version, which will ultimately make our math a whole lot easier to deal with. So if I look at figure 3.3, and we were just dealing with 3.3 at the end of lecture, and I said, hey, we've got several steps here going from state 1 to state 2 to state 3. Basically, state 1, the path from state 1 to state 2, and from state 2 to state 3 are actually two hypothetical paths. The real path would be from state 1 to state 3, the irreversible path that we're trying to analyze. But because entropy is a state function, it can be path independent, so independent paths, I can add two hypothetical paths together. First path I'm going to do is state 1 to state 2. So I have my delta S is going to be my final state, S2, minus my initial state, S1. I'm going to integrate with respect to squirrely dq reversible divided by the temperature of the surroundings. Surprise, surprise, when I have dq equal to 0, then my integral has to be equal to 0. So a reversible adiabatic expansion process, remember, if we're expanding the gas, the pressure has to decrease. That's going to be a 0 entropy change, a 0 joules per mole per Kelvin. That is a kind of a new discovery here, but it's a normal consequence of what we're looking at. If I were looking at the first law, where I have delta U is equal to W plus Q, Q is equal to 0, then I'd have delta U is equal to the irreversible work of that process, or the reversible work of that process. Now, there's my adiabatic process. It is also isentropic. You're going to see this coming up through here. When I say adiabatic, I am simultaneously saying that the process will be isentropic. And that's just by the nature of the Clausius equation between ds and square dq. Okay, so the big thing was, okay, let's add that second hypothetical path. That's a temperature increase, an isobaric temperature increase. Heat needs to be added to the system, and that heat added to the system will raise the temperature from T2 to T3 for the irreversible process. So I got my hypothetical path, S1 to S2 to S3, which means two processes. Each one of these arrows, right, is a process, so I've got two processes in there. And I know that for an irreversible process, delta S has to be greater than 0. Q is still equal to 0 because this is adiabatic. So I would start looking at this from S3 to S1. I'm going to have a net entropy increase. So delta S of the surroundings is equal to 0 because, again, there was no exchange across the boundary of heat in this adiabatic system. But inside the system, the entropy exchange happened, and we have delta S of the universe greater than 0 because we're reflecting the system addition of that as being positive. I'd recommend to go look at figure 3.3 and start working through these problems, compare them with the last lecture notes. Okay, so now, thinking about that again, I go from S2 to S3 as my hypothetical process. Delta S should be greater than 0. It's an isobaric system, isobaric process, hypothetical process. It's a transfer of heat into the system. And so ultimately, I've got to figure out where I'm going to get that extra energy from and how do I calculate that energy. This is from our notes last lecture. The process is not going to be isentropic, right? Delta S is not equal to 0 because in the integral that I'm going to be doing for 1 over t is going to be the natural log of T3 over T2 times Cp, right? So I'm going to have the integral of 1 over x dx is going to be, of course, natural log of final state over initial state. And the units are going to be joules per mole per Kelvin, same as entropy. Again, this is review. The process, that hypothetical process from 2 to 3, is a horizontal line on figure 3.3. That means it's an isobaric process. I can use an isobaric heat capacity term, Cp, an intensive term. So what I'm going to get is delta S is going to be equal to Cp times natural log of T3 over T2. If I want to turn that into the extensive form, as you're seeing in blue here, of delta S extensive, then I'm going to need to multiply in the total number of moles to turn my units into joules per Kelvin. If I were now to look at the next figure is, okay, great, you've done an adiabatic irreversible expansion. Let's look at an adiabatic irreversible compression step. Now, if I compress a gas, the pressure has to increase, which is what you're seeing in figure 3.4. But do you notice my hypothetical paths as I go from state 1 to state 2 upwards? And then I go from state 2 to state 3, right? I am ultimately increasing in temperature. And that state 2 to state 3 is an isobaric process, another isobaric process, where I'm just going to do the same integral that I did, same type of integral that I did for 3.3. Meaning that I'm going to have adiabatic expansion, delta S greater than 0. Adiabatic compression is not going to be delta S less than 0. It's shifting the whole system to the right. I'm increasing the temperature of the system again. So of course my delta S is going to be greater than 0 as well. Let's look at that here. Yeah, if I have an integral of the two equations where the two parts of the hypothetical path are basically just the temperature increase from state 2 to state 3, they will both be positive values because the hypothetical paths for the reversible processes, the parts that are expansion on the left, the part that is compression on the right, those are reversible parts and they have a delta S equal to 0. So both are going to be positive values. Again, this is one of those things where you might want to pause, think about this, look at how the two hypothetical paths are put together because you're ultimately getting something pretty rewarding. Next task. I mentioned this in the notes. I want you to work the Carnot cycle case 2 on page 137 and it's going to be a case for the delta S of surroundings. And I think the part that's going to be really challenging here is how do you connect together the math for surroundings, which in fact is the negative sign of following the math for delta S of the system. This is example 3.1 and it revisits section 2.3 from Koretsky. When we're doing that, if I look at this snippet from that section of the Koretsky text, we see that a cyclic process, right, the net energy is going to go from state 1 to state 2 to state 3, back to state 4, back to state 1. So I start at state 1, I end in state 1 because it's a state function. You could think of that as 1, 2, 3, 4 hypothetical paths that lead you back to the same state, making the entropy, the energy change, internal energy change of the cycle equal to 0. Similarly, it's a state function of entropy, so delta S of the cycle is going to be equal to 0. This, as a reminder, this does not mean that no work is being done or that no work is required. This just means that the state functions are behaving like state functions. All right, so the entropy change to the surroundings is going to be what we're looking at here. You'll see that ultimately in this process of looking at the Koretsky work, that the entropy change for the surroundings is closely associated with heat, because it's always going to be heat, Q, divided by the temperature of the surroundings, whether the surroundings are hot surroundings in the isothermal expansion process, or whether the surroundings are going to be cold surroundings as a reservoir in the TC variety. Negative signs here are used for Q because the heat transfer to the surroundings is the negative of heat transfer to the system. Basically, this is what I'm saying. It's like it's worth reading this because the math is flipped there. This is Koretsky is shifting where the ball is. He's saying, okay, now keep your eye on the ball. The ball is the surroundings. It's not what I prefer to do, but I want you to know what this section is stating and that this is simply a reversal of the math that you guys have been doing for the beginning of the semester. If I look over on the right side, you're going to see that my equation for Q hot, right up here for the process that is isothermal process, that's equation 3.5. That's going to be negative RTH, the temperature of the surroundings, times the natural log of P2 minus P1. Similarly for the, that's the expansion side. For the compression side of this from 3 to 4, we have the natural gas constant times T cold, that's again the temperature of the surroundings, times the natural log of P4 over P3. And the negative part of that is, again, because we're looking at this in reverse. Okay. If you look below that, it describes the two adiabatic processes. And this is what I want you to look at, is really the format of the equation, because this is a way that the author is showing you how to use this adiabatic equation, PVK to the constant. And what he's actually doing is he's separating variables between pressure on the left side and volume on the right side. He is substituting pressure variables for ideal gas relationships so that it can just have temperature and pressure on these, on the right side, sorry. So now I have pressure and I'm substituting for volume to get nRTC times pressure to the K, right? And ultimately rearranging the equation to solve in terms of pressure relationships to temperature. Once again, you might want to go back to your textbook, look at these, work these problems, and start seeing what's happening. The tricky part is, again, that in this particular section, you're getting the opposite sign of what you're looking for, yet the math still holds, and it's still very important to review. Okay. Ultimately, I've still got my delta S for my hot process, my delta S for my cold process. If I add them together, I'm going to get them equal to 0. The other two processes, of course, were adiabatic, and thus were already 0. This isn't two adiabatic processes. You don't need to include them because there's no Q involved. And the only way I can represent the second law is with respect to Q over T, or delta, or dQ over T. All right, moving on. For an irreversible cycle, right, we start with reversible cycles and then we try to make them more complicated. We try to say, okay, how do we deal with an irreversible cycle based on what we know about reversible cycles? So for an irreversible cycle, delta S of the cycle is not equal to 0. Okay, you don't end up where you start. In fact, you end up in a totally different new space, new energy space, new entropy space. For an applied understanding of what I'm talking about in this area, I'm really going to highly recommend that you go to Koretsky and you work by hand examples 3.2, 3.3, and 3.4. Those are for closed systems, but it's still key math for your fundamental understanding in this class. And when I say work the examples, I really do mean write them out by hand and start seeing how these are tied together. I do not mean reading the examples. Work them. All right, it'll be good for you. Now, if you note here the role of heat capacity in hypothetical paths, there's a big part of heat capacity in all of these equations because there's always going to be a reversible path that is going to be a delta S equal to 0, and then tied with that is going to be another additional hypothetical path associated with a sensible heat change, say at constant pressure. Additionally, look in these examples and note the use of the first law. That's du is equal to squarely dq plus squarely dw. We're not having non-mechanical work in here. Integrate that and I have delta u is equal to q plus w. Pay attention to those constraints. And remember that we've got, some of these are going to be systems constraints. The entire system might be well insulated. Some of these might be just a process constraint. The process happens adiabatically. If I now go back to Chapter 2, I believe it's page 95, very important page, page 95. Look at Table 2.2, and I see that there is my values of Q for an isothermal process and an adiabatic process. Remember, Q is critical to the definition of the second law of thermodynamics. If I were to look at this, I would say, okay, well, given that in an isothermal process, Q is equal to minus n over RT natural log of P2 or P1. In order to get to delta S, I'm effectively going to divide out that temperature. That's what gets us a delta S is equal to minus n R natural log of P2 over P3. This is basically dividing the value of the isothermal process by T, and the T drops out in terms of an entropy relationship. You could flip that around in terms of volume. I encourage you to look at this yourself and get the positive NR natural log of V2 minus over V1. Of course, if that minus sign were maintained, it would be V1 over V2, based off of the mathematical principles of a natural log. Feel free to pause this at any point in time to go back and take a look at what we've been going through. This is just a reminder. Now, delta S for that isobaric process. Now, there's an isobaric process. That's not a part of what you're seeing in Table 2.2. And an isochoric process, well, that's not a part of Table 2.2 either. Yet, they are terms for which we have an equation, a heat capacity equation, where we're integrating with respect to temperature change. And you're going to find that we're going to incorporate these two questions, these two equations, into our solutions. That the entropy change of an isobaric process is going to be the number of moles times the isobaric intensive heat capacity times the natural log of the final state T2 over the initial state T1. And similarly for the isochoric, but we will be using the isochoric intensive heat capacity term. All right, last thoughts here are going to be introducing core thermodynamic concepts of energy conversion devices. What is it that one cannot do in thermodynamics? This is kind of like, okay, so thermodynamics can do a whole lot, but there are certain things we can't do, and we've already encountered one, and we encountered it through the first law of thermodynamics, and we expressed it functionally in an energy conversion device as a perpetual motion machine of the first kind. Now here, what we have is a relationship where early research into thermodynamics associated with heat passing from colder and hotter and hotter and colder bodies. We have basic research by Clausius that shows that in 1865, Clausius reports that heat cannot pass from a colder body to a hotter body without compensation, right? Without energetic pumping of that energy from cold to hot. We already have these in air conditioning units and in refrigerators. But Clausius in 1865 identified that heat doesn't just spontaneously jump from a cold body to a hot body. You need compensation. You need some sort of energetic compensation to make this happen. This is essential to modern thermodynamics, which is a core part of this class. I will fully acknowledge that in the Koretsky text, it's not addressed as such. And so we're bringing this right up front in the lecture notes. The second side of this is that Thomson, also known as Lord Kelvin, and Max Planck in 1846, well, let's start out with the fact that in 1846, Lord Kelvin coins the term thermodynamics to associate heat and power. He develops this report of Carnot's modern theory of the motive power of heat. And remember how Carnot, at age 28, produces this wonderful report about the Carnot cycle, and nobody notices it. Well, by 1846 and later, Thomson and Planck start really noticing these things, and Thomson develops an account of Carnot's modern theory of the motive power of heat. Both of them together come to the conclusion that it's impossible to make a heat engine. This is like engineering sense. It's impossible to make a heat engine where I only have work going out, where there's no heat losses, no Q out. It's impossible to make a heat engine that is 100% work output. And the way to look at this in terms of thermodynamics, in terms of the way that we define an irreversible process, is it's impossible to have a heat engine with no dissipation of energy. So if I don't have a heat engine, I basically can't have a heat engine where I have no dissipation of energy, or I can't make a perfect heat pump. Clausius's other side of that, or heat engine, Clausius's side of that, is that I can't have a perfect heat pump. So what you're seeing here between Clausius, Thomson, and Planck, and what I will refer to in the next lecture as well, is that what you can't do in thermodynamics is you can't have a perfect heat engine where there's no dissipation of energy, and you can't have heat, spontaneously jumping from a colder body to a hotter body. That would be an impossible heat pump, or a heat pump that required zero work. All right, so good lecture materials today. I'm going to encourage you to go back, think about these concepts, do both the Koretsky reading and the supplemental reading. Pay attention to your Canvas announcements and reading assignments, and we'll talk to you next lecture. Thanks so much.